In this section 5.2, we will go over the derivative of the general exponential function, which is represented by y equals b to the power of x. Previously, we explored the exponential function y equals e to the power of x. So if you don't know how to do that and if you want to get familiar with it, we also have a video on that. And in this section, we will go over the exponential function y equals b to the power of x and its derivative, where b representing any number. So when we encounter an exponential function like the b to the power of x, if we want to take the derivative, we follow this formula right here, which is ln b times b to the power of x. So let's say, to understand it better, let's solve this problem, which is saying determine the derivative of fx equals 5 to the power of x. Now, we said b can be any number. So in this case, my b is 5. So, and then I have 5 to the power of x. I know when I look at the derivative, if I want to take the derivative of this, all I need to do is write ln and put my b value, which is 5. So I have ln 5 times whatever is your b to the power of x is, which is 5 to the power of x. And that's it. That would be your answer. So let's say it's not given as a simple b to the power of x. Now what if you had gx in the place of x? Then just like the exponential function y equals e to the power of x, we keep gx, that is the power of b, but instead take its derivative and multiply it. So let's say if we were to take the derivative of 5 to the power of 3x minus 2. I know my gx is this. So I know my gx is going to be 3x minus 2. And I know at some point I need to take the derivative of it and multiply it. So I will be taking its derivative directly. And I know from 3x over here, it's when I take the derivative, it's just going to become 3 because it's x to the power of 1. And I know because negative 2 is a constant, it's just going to become 0 when I take the derivative. So now that I have my derivative for gx, all I need to do is plug in back into my formula. So normally when I take the derivative, I said it's b to the power of x and ln b. We still keep that in the formula, but instead we apply it to the gx. So that's why we have the derivative. So if I do that, it's going to be 5 prime x, and my b is 5, and my gx is 3x minus 2. And I'm going to put ln 5, and then my derivative over here, which is 3. To make it look easy, you can also just change up the 3 and put it into the front, which I usually do, but it doesn't matter. So your answer will be that. So let's start with the word problem. On January 1st, 1850, the population of Gold Rush Town was 50,000. The size of the population since then can be modeled by the function pt equals 50,000 0.98 to the power of t, where t is the number of years since January 1st, 1850. So I already know that this function represents the population since 50,000 people. That's my population, and as time it represents right after 1850. So when it says the first part, what was the population of Gold Rush Town on January 1st, 1900? So I know that I have 50 years in between these. So if this is my first point, and if I count 1850 as 0, then 1900 would be my 50th point because they're on the same date as well. So my in years, since t represents the years, I can directly put that into my time variable right here. So all I need to do to find my population, because that's what it's asking for, is to plug in 50 for my t value, which will give me 50,000 0.98 to the power of 50, and if you plug that in back into your calculator, you will end up with 18,208.484, and that will be your answer. But if you round it, it will come up to 18,209. So the second part is saying at what rate was the population of Gold Rush Town changing on January 1st, 1900? When it says what rate, I already know it's asking for the derivative of this. And it's saying was it increasing or decreasing at that time? So as for the second part, I'll start by taking the derivative of my function right here. Let me erase a few things to make it easier on you too. So right here is what I'm taking the derivative of in order to find the rate. So when we're taking the derivative of pt, I know the first part is a constant, and remember we're always keeping the constants. So I will just say 50,000 and then separate and apply my derivative to this part, which is 0.98 to the power of t. So when I do that, I will get 50,000 again. And remember, this is in the form of b to the power of x. It doesn't matter what b is. In terms of this, my b is 0.98 and my x would be t. And I know b to the power of x, when you take the derivative, it will be ln b times b to the power of x. So here, what I'm going to do is saying times ln, and my b is 0.98. So that's what I'm going to put. So ln 0.98 times b to the power of x, which is 0.98 to the power of t. So now, because it wants the point where it's changing on 1900, which I know my t is 50, because that's what we did for part A as well. So I'm going to go ahead and plug in 50 for my time to find if on that exact same time what happens to my population. And from there I can see if it's increasing or decreasing. So I will be saying 50,000 ln 0.98 and then 0.98 to the power of 50, and plug that into your calculator. You will end up with negative 367.861. And I know now that it's decreasing. So obviously we cannot have 0.5 people, so I will be rounding this to 368 people. So we can say that the population was decreasing at a rate of approximately 368 people per year. In this question, it's saying if ft equals that, determine the values of t so that the derivative will equal to 0. So I already know if I want to determine the values for t that my derivative equals to 0, first I need to find what my derivative is for ft. If I find the derivative and equal it to 0, I'm going to find what my t values are. So if we start by taking the derivative of ft first, I know because these are times, I'm going to apply chain rule. So if I call this my ht, and let's say I call, let me find a color, let me call this gt, it's going to go like, I take the derivative of ht first, keep gt the same, plus keep ht the same, and then take the derivative of gt. So if I go with this, I know the derivative of ht is in the form of b to the power of gx. And I know that if my gx equals 3t minus 5, I need to find the derivative of my gx, which will equal to 3, because if you look at this portion, this is t to the power of 1, which will just become 1 when you apply the power rule. And since this is a constant, it's just going to be 0, and this is my derivative for gx. Remember what I said for b to the power of gx? What we do is keep it the same, so 10 to the power of 3t minus 5. Apply ln b, so I apply ln, and my b value is 10 in this case. And then multiply it by the derivative of gx over here, which will be 3. Now I keep gt the same, which is e to the power of 2t squared. And then I do plus For ht, keep it the same, don't do anything, so 10 to the power of 3t minus 5, and then take the derivative of gt. So don't get confused by this. This was separately for the formula. They are not the same functions. I should have called it something else, but in the formula we usually say gx, so that's why I said it to make it easier on you guys. So for this one, if I take the derivative of gt, I know it's in the format of e to the power of g x again. So if you think of it like that from the formula. And for this formula, we said e to the power of gx will equal to the same thing, but times by the derivative of gx. So no lns. Lns are for the b. So this is actually from the previous section. So I know from here what I'm going to do is keep e the same and then take the derivative of 2t squared. And if I take the derivative of this, I'm going to keep the constant in the front, apply the derivative to t squared, and if I apply the power rule here, all I need to do is bring the power to the front, which is 2 over here, keep t, and do minus 1 to the power, which will give you 1. And if you multiply these two together, you will end up getting 4t. So now I'm going to multiply here by 4t. So now if I equal it to 0, whatever I have, I can actually cancel a few things out by putting this value as negative to the other side. So when I do that, I see that this section over here is automatically negative for everything because they're all in multiplication form. And I see that since this is positive and here is negative, not even that, I can just divide both sides by 10 to the power of 3t minus 5. So when I divide them, it's just going to cancel out. And I know from here, I can also divide each side by e to the power of 2t squared because I see that I have it for both sides, which will cancel these two out. So now that I end up with this, since I want to find what my t value is, I'm going to leave t alone by dividing each side by -4, which will cancel this one out. And as a result, I get t equals 3 ln 10 all over -4. That will be my answer. So a certain radioactive material decays exponentially. The percent P of the material left after t years is given by this function right over here, and it wants us to determine the half-life of a substance. So you guys are going to see a lot of half-life problems in the future too. What half-life means is the half of what your original value is. So it wants me to find what is the half of my original value of this substance specifically. So I can first find how much I had initially and then do divide it by half to make this equal to half-life. And then what I need to find is, because it says determine the half-life, I need to find whatever the t is. So because I want to find whatever is the initial value, I'm going to count t as 0 because that's my initial point. So if I do that and plug it right into my t, I'm going to get 101.2 -0. And because here we have 0, this whole thing is just going to cancel out to 1, which will equal it to 100. So my value initially is 100. So now that I want half-life, I'm just going to divide that by 2, which will give me 50. Now that I have my half-life value, all I need to do is, in order to determine the half-life of this substance, is I'm going to make this equation equal to 50. So I'm going to go ahead and say 101.2 -t will equal to 50. Now, in order to get what my t is, because that's what I'm trying to find, I'm going to divide both sides by 100. When you do that, these two are going to cancel out. So over here, I have 1/2 left. So now that I have my 1.2 -t, which will equal to 5/10 or 1/2, from here, what do? I can take lns of both sides, to get this t. What I mean by that is, in case you guys don't know what I mean by that, is when you take the ln of anything in this form and what you're trying to find is the value of the power, you're trying to bring that power down. So if I take the ln of 1.2 negative t, and I take the ln of 1 over 2 too, because I need to take the ln, when I take the ln, I need to take the lns of both sides. There's actually a property where when you have ln and a value over here to the power, you can bring this power to the front of the ln. So if we do that, we're going to end up with negative t ln 1.2 equaling to ln 1 over 2. Now that I have my t, it's so much easier to find what my t value is, because I can leave this alone now. I can divide both sides by ln 1 over 1.2, and I'm going to get negative t equaling to ln 1 over 2 over ln 1.2, which I'm going to bring that negative over here to get rid of this negative over here. And my value, if you put it into your calculator, is going to end up being 3.8. And because my t represents years, that's going to be in years as well. So the second portion is saying how fast is the substance decaying at the point where the half-life is reached. Because it says how fast, it involves the rate, so rate of decay. And whenever we say rate, it involves taking the derivative. So what I'm going to do in order to find that equation where I can plug in my half-life point, because it's asking for specifically where the half-life point is, where I can plug in back into my derivative. So first I'm going to end up taking the derivative of pt, and I know because I have a constant over here, I leave it as it is and then take the derivative of this portion right over here. What I realize is it's in the form of b to the power of x. However, remember that because it's a negative x, you can count it as b to the gx, because you can technically take the derivative of negative 2 because it has a constant. So this negative is actually negative 1x. So it's considered to be gx. So when you're taking the derivative, it will equal to b gx ln b and multiplied by the derivative of gx. So now when I'm taking the derivative, what I'm going to do is keep it the same first. So 1.2 negative t. Now I'm going to do the ln, which is ln 1.2, and then take the derivative of gx, which is negative t. This is basically the same thing as saying negative 1t, and this is to the power of 1. I know anything to the power of 1, when I take the derivative, it just becomes 1, so I'm left with negative 1. So I have negative 1 over here. I'm just going to erase this really quick. And from here, I can just simplify it a little further to get negative 100 ln 1.2 and 1.2 negative t. Now, all we need to do, since we have whatever the derivative equation is to plug in my half-life. So what I mean by that is we found that half-life is reached at 3.80 years. So since I know this is the t value, all I need to do is plug in 3.8 for my t value. So now I have negative 100 ln 1.2 and 1.2 to the power of negative 3.8. If you plug that into your calculator, you will end up getting negative 9.12, and you can say it decreases by % per year. And that will be your answer.